All right, now we have Cindy and Barbara. You got a hard act to follow there.
Yeah. There we go.
All right, if you could just take a little break, please, and put so we could have Cindy and Barbara. You could continue your projects during lunch.
All right. If we could maybe take some seats here so we can get started, and then we won't be late for lunch. Because, yes. Excellent. All right. Yeah, so we're going to shift gears and do our fireside chat. So thanks for having me back. I am so excited to have my teammate Barbara Brown. If the conversation today with Barbara is going to be anything like our Teams calls, it's going to blow your mind, truly. We are doing so much to live on the moon, and so we're very excited about that. This morning we heard from our teammate Joe Dant, who provided some conversation about commercial space, new technologies, and rockets. And we talked about how educators can help prepare students for space careers. But we're going to shift gears and get into the nitty-gritty parts of why we're going back to the moon with Artemis and what work is underway for living there. And again, we're so grateful to have Barbara with us, who's the Director for Exploration Research and Technology Programs at NASA at the Kennedy Space Center over in Cape Canaveral. And Barbara, your title is like loaded, right? And can you kind of tell us more about what you do?
Sure. First of all, I want to say how happy I am to be here. I'm really excited. I am a frustrated teacher and educator. I wanted to be a teacher, but I wanted to work for NASA too. So occasionally I get to come to events like this, and I try to go into schools as often as I can to mentor and help inspire the next generation that will come behind us. So my title is a long-winded title, and I wear a few hats for NASA. One of the hats that I wear, my primary hat, if you will, is to make sure that everything that needs to go up to the International Space Station is checked out, packaged properly, and then taken over to the vehicle that launches it to the International Space Station. So basically, my job is one, to make sure that all the processing, the integration, the assembly, the testing, all those types of things are done. And what we send up, it could be hardware, might be logistics, replacement supplies such as food or water or batteries. And then sometimes, hopefully most of you have seen evidence of the experiments that get conducted on board the space station. So one of the things that we also do in my group is make sure those experiments, or we call them payloads, they are also prepared and packaged in a way that will protect them so that when they get on orbit to the station, they function when they're opened up. Some of those experiments could be science, they could be related to medicine, they could be related to 3D printing, etc. So those are the main two hats that I wear. And then I also have the honor, the privilege of being involved in what NASA calls its Artemis program. And for Artemis, we are going back to the moon and we're going on to Mars. Yes, I'm so excited about that. And so my other hats are involved with understanding what types of roles that we need to have prepared, what your students and future generations will need to be able to do so that we can live and work safely and thrive on the moon and Mars and wherever else we may want to go. So that means I and my team are thinking about what we know how to do at the Kennedy Space Center. I had the privilege also of working the shuttle program. And I and most of the people that work there, we feel like everything was a privilege because we're space nuts. We're sold out on what we do. So it's one of those things where you feel like I would have paid them to let me come, but they ended up paying me. So it's just awesome. But with the shuttle program, what we had to do for years was think about how to sustain that operation. A lot of the missions that have gone to Mars or to other celestial bodies, they are designed to operate for a brief period of time. Now, we're happy when they continue to work beyond that period, but shuttle program was sustained for a long time. So that means we had to think about how do you keep the systems that are needed to fuel it, to operate it, to check it out. How do you keep them going? And with the shuttle, for example, same thing's going to happen with us with the Artemis program. The shuttle used super cool cryogenic fuel, hydrogen and oxygen, minus 300 degrees, minus 400 degrees. So when you think about your car, if you put those types of fuels into your car and then pressurize your engine at 100, 200, 300 PSI, it's very easy for the seals and the joints in your engine to either fracture or leak. So if some of you recall with the shuttle program, we often had delays. And a lot of those delays were around the fact that we had these exotic fuels, this very complex system of hardware that was prone to all types of faults that could occur. So we spent time understanding if we were safe to launch. So we have to think about those same things here on Earth. It's going to be even more difficult when we get to the Moon and Mars because we'll still have to think about how to survive and how to keep the operations sustained over a long period of time. So we get to take our knowledge in ground operations and apply it to surface operations. So my other two hats revolve around taking that knowledge and translating that into what we need to be able to do and the people that we'll need to support those operations or the robots that we'll need to support those operations. So those are all the hats that I wear for NASA.
It sounds like a lot of hats.
It is.
It's a lot of hats.
But it's fun.
Yeah. So you mentioned 3D printing, which we heard this morning. So another thing that, I know some teachers here are doing that. You saw some of the projects.
Yes.
Actually, so, you're welcome to take our ideas back to your team and, have those help.
We'll try to give credit.
Yeah. Okay, so Barbara, why are we going to the moon?
So we're going to the moon because we really, for those of you who saw the video, was it yesterday?
Yeah, yesterday.
That we're going, some of this will just be a little bit of a regurgitation, but we're going for a number of reasons. We're going for the science. We need, as NASA, one of our roles is to expand human knowledge. We want to understand how planets and celestial bodies age. We want to understand if humankind can live beyond lower Earth orbit. And I say if because, as you all know, I saw at some of the tables, there is a very real risk of radiation and what that can do not only to humans, but to the plants that we would need to grow. Radiation can damage the electronics as we're trying to get there and when we're there. So we're trying to understand how to allow humankind to explore beyond the bounds of lower Earth orbit. We're also going because there's going to be great economic benefit. The moon is full of all types of commodities, elements, minerals, whatever you want to call them, that have economic value. So there is a strong commercial aspect to going back to the moon as well.
Yeah, and we have been there before. So what's different now?
So this is where I really get excited because, I was a very small girl when we went to the moon the first time, and I was just thrilled then and wanted to know how I could get involved. And I remember telling my parents that NASA needed me. And I remember my mom just kind of laughing and saying, okay, Barbara. But I was kind of blessed that I was able to work for NASA. But what's different, some things are the same. We're still going for the science. When we went before, we went to expand human knowledge. This time, though, we're going back because we have plans to stay. When we went before, it was, can we do it? How would we do it? And how do we make sure those astronauts get back home safely? This time, we're going with the intention to sustain our operation there, as I mentioned earlier. And then the really exciting part is, as we go this time, we will be landing not just the next man, but the first woman and the first person of color. So that's like, yay! We get the cake, the icing, the candles, and fireworks all along with it. So as you can tell, I'm really excited about the fact that I get to participate in this endeavor.
There's no passion on the stage about this at all.
So this, what you're seeing now, this is the initial crew that has been selected. These are the candidates. We have not identified which of them may be on the mission and the first to go back to the moon. We usually select crews 2 to 3 years before a mission. We'll select the crew and then the backup that would go in case something happens to one of the primary members. So you're looking at the candidates that could one day be the next to walk on the moon.
So exciting. It's a 62-year-old guy over there wants to go.
Okay, I'll get your card before I leave.
I did want to call out one in particular. At the top left, we have Joe Akaba. He is a former teacher, was hired by NASA in 2004, so he is going to the moon, possibly. All right, so Barbara, how does this all work? How will we get there?
So we have a number of elements that are involved in the Artemis mission. And so you know that Artemis will go to the moon, will go to Mars, but how do we get there? We need the Space Launch System. That is the vehicle that will take us, the supplies, and the crew back to the moon. You see at the top on the left is the integrated vehicle. That's what will go to the launch pad and launch with the crew on top. Next to it, you see the Orion capsule. That's where the astronauts will be during the launch. Very much going back to what we did as the architecture for Apollo. We will have a landing system for the humans, for the crew to get off of the vehicle once it lands. And then we will also have spacesuits. We're looking at new improved spacesuits from what we've had in the past. That's because we've learned from our experiences on the moon before. We realize, as someone was telling me at the back table, there's space dirt or regolith, as you know it is. It is abrasive, it's hazardous. We found during the Apollo mission that it scratched everything it touched. It was invasive, it got in all the joints. If you think about plugging your phone into the wall to power it, think about dust being all over the end of that plug or getting into the connectors. So that regolith can cause all kinds of problems. It scratched the visors of the helmets. And also, if you remember how the astronauts moved when they were on the moon, they didn't have a lot of flexibility. So we're looking for a lot of improvements in the spacesuits. We'll have the gateway, which will function. It'll orbit around the moon. It'll orbit around the moon, and it will function much as the International Space Station does today. We've got the vehicle at the top of that page. Beneath it, you see the vehicle assembly building at the Kennedy Space Center, where I work. That's where the rocket is actually integrated. All the different elements are brought together. The rocket, the solid rocket boosters, the Orion capsule, etc. And then we're going to need communication. I saw someone had that on their table back there. And other elements will be involved in us getting back to the moon and then eventually setting up what you see in the lower corner on the right, the Artemis base camp, which will be at the South Pole. Now, this is a video of the first rollout of that vehicle. I had a chance to be right there to see it. It was amazing when you talk about taking about 1,000 pictures, because I was like, okay, take a picture now. Okay, take a picture now. So get a picture of me, now take another picture. And everybody, there was a huge crowd there. And this is actually the vehicle on its way to the launch pad. The Exploration Ground Systems Program, or EGS, is responsible for all of the launch operations for the vehicle for the Artemis program, and it was on its way out to the launch pad for what we call a wet dress rehearsal. The wet dress rehearsal means that the team is preparing the vehicle for launch. They're stepping through all of the launch preparations. even to the point of fueling the vehicle and making sure they understand everyone at their station and knowing what to do when we actually are in the real launch countdown. This is just to show you the magnitude of the enormity of this system. If you look down at the bottom next to one of those big treads is a person with a red shirt on. That's how big this is. The crawler has the treads at the bottom. On top of that sits the mobile launcher, and on top of that sits the rocket itself. And so it is massive. The crawler itself is as big as a baseball field. So you can imagine something that big up 25 feet in the air that you could walk underneath it. Just astounding.
And I can only imagine, as you're anticipating all this technology going to the moon, that there's challenges involved. And these teachers have experienced challenges in the last couple of years also. So what are some of those challenges that you've been focused on solving? So
I really was excited going to some of the tables because you guys are hitting. I see you've done your research. Some of those challenges, the main one we think about is radiation. We also have to think about, as I mentioned, not just protecting the humans, but also the food that we will grow, the livestock, whatever animals we might end up wanting to have at the moon. We also have challenges with communication delays and just the fact that it is a hazardous environment. We are blessed to be here on Earth because when we walk outside, we don't have to think about all the equipment that we need to have to protect us. So those are just some of the challenges. Another challenge is the isolation. It is hard on humans to be separated from other humans for a long period of time. And what we're finding, even with space station, it's hard for humans to be separated from Earth. The astronauts enjoy just going to look at the plants that are being grown, just to have connection back to planet Earth. So Cindy, if you would go back a couple of slides, I wanted to point out on this one, what you see here, I thought you might enjoy seeing a comparison of just how big the vehicle is. So the one in the very middle, that is the Artemis rock vehicle that you saw roll out. And so it is much taller than Shuttle, and if you had a chance to see Shuttle, that was huge. That rocket is the only rocket that has enough thrust to take what we need out to the moon. One of those rocket boosters, which are the twin boosters along the side of the orange, just one of them has enough thrust to lift 20 elephants. It's like 20, I think I said that wrong. The vehicle itself has enough thrust to lift those elephants. One of those rocket boosters, however, could probably lift about 20, it's the thrust of about 22 747s. So the thrust itself is going to add up for that total vehicle at 8.8 million pounds of thrust. That's enough to get 42 F-150s into orbit. I drive an F-150, so that was interesting to me. Okay, so, and then for the Artemis, the priorities that we have, what we're going to do with this first mission, which should go sometimes later, no earlier than the end of August. It's a test for us. We're going to have a couple of mannequins on board that are instrumented. They're going to be taking measurements on radiation. We'll also have opportunities to test out the vehicle itself to make sure the heat shield works the way we think that it should work on reentry so that it'll protect the astronauts when they land. We're going to exercise all the systems and just make sure everything's functioning properly. We'll also send some secondary payloads, which are basically science. Some science related to how does radiation affect seeds, because we'll want to take seeds with us to grow plants. We're also looking at comm and other types of payloads that will go.
And I know you mentioned some science and technology objectives, so maybe you could talk a little bit more about what is it that we're going back to do there in terms of science?
Sure. So with the science, we are still embarking on that quest of understanding what is the history, how does a planet or a celestial body evolve. We're going to be looking for water. We're going to be looking for other volatiles that we can use to manufacture oxygen, carbon dioxide, and other elements that we'll actually need to produce what we need when we go. One of the focus that we have is to try to take as little as possible with us, because the more you take, the more you put in that vehicle when you get ready to launch, the more energy, the more thrust you need to get it off the ground and out of Earth's gravity well. So we're looking and investigating early to understand what's there and how we can best use it, and then how we can mine other things that could be used commercially.
Right.
And then from a technology standpoint, I mentioned that we're trying to take as little as possible when we go. That translates into what we call in situ resource utilization, which is just a fancy word to say make what you need when you get there. In situ, once you're there, utilize what's there. So we've got a number of programs and projects across NASA, which is spread across the country, actually thinking about how do we 3D print? How do we find the materials that we can use in the 3D printers? How do we grow plants in the regolith? And everything else that you can think of. How do we get oxygen and the other elements that we need to manufacture fuel that we could use to return back to Earth once we're there? So these are just some of the areas. I already talked about dust. That regolith creates the dust, and we're looking for ways to dampen the effect or eliminate the effect of that dust. It is an extreme environment, so we're looking for technologies that help us survive in that environment, and also thinking about when we get there, how do we build, how do we excavate? My team is involved in a number of these activities, from the in situ resource utilization, dust mitigation, and also excavation and construction. I'll have a video a little bit later to show you one of the robots that we use.
And I know that you mentioned something that Gateway will be used, something like the station. I know station's a big part of your job. Can you explain a little bit more about how we use the space station now?
Sure. The way we use station now is as an orbiting laboratory. It is considered a national laboratory. You see here on this slide all of the partner agencies that work with us. And we do everything from understanding how humans can work in low Earth orbit, where they're largely protected from the radiation by the Earth's atmosphere and magnetosphere. But we still have areas in the station where they are shielded in case of flares. We're understanding how to conduct science and research in space. I talked about the science payloads that go up. We're learning what you have to do to keep humans healthy. So they have sleeping quarters, they have working quarters, they have an area to do exercise. So we're literally using it to investigate everything that we can within low Earth orbit. And then the station is really becoming essential for the Artemis program, which is to think about what can we learn, what have we already learned that would be beneficial and could translate to being used on the Gateway, because the Gateway will orbit around the moon the same way the station orbits the Earth. So we'll be using it as an outpost, if you will. It'll be placed for us to congregate elements that are needed for the astronauts that are going down to the moon, to congregate supplies, to conduct research. So it'll have labs. It'll have the same things, but on a smaller scale than the station has.
Mm-hmm. And that's something that I hear often is, why do we need Gateway if we have the space station? Space is huge. We need something close to the moon.
Yes. The station orbits around the Earth, so it's really too far away to be beneficial for what we're going to do on the moon. Yeah. And for those who've never thought about it, this is actually how big the space station is. You don't really think about it. We sent it up, and I actually can remember signing before we sent some of those trusts up. We had an opportunity to sign, so my signature is on one of those trusses. I don't know which one, but you don't think about it when you see them as little, almost Lego building blocks. I mean, they're still huge Lego building blocks, but to think about it covering an entire football field. And just an interesting fact, when the station orbits the Earth, it's actually going 17,500 miles an hour. So it sees 16 sunrises and 16 sunsets every day.
The ultimate need for speed is
Yes.
right there.
I used to say
I'd
I'd...
Top Gun, actually, right?
That's right.
No.
Yeah.
Yeah. And that's pretty small to live in for, 6 months or a year.
Yeah.
You don't get to go to the
Yeah.
mall or the park.
Right. And not all of it is livable space. As you can see, the black parts, those are solar arrays. And the white part down the middle, that's the truss or the backbone of the station. So, but it's been operating for more than 20 years, so we're really proud of that accomplishment as well.
And Barbara, I know one of the things I've enjoyed about our conversations is this next part that we're going to talk about. How many of you have planned for a long road trip or a camping trip? Okay. Probably one of the things you think about, maybe the most, is you got to take snacks, you got to take food. We're going to the moon, so that's a really big consideration
Yes.
of how do we do that. I've just really enjoyed these parts. So how are your teams preparing for this aspect of the mission, and what will this look like on the moon?
Right. So, again, I get the privilege of leading a group of people that are actually responsible within NASA for growing the plants in space. We start first with what we can do on the space station. And then you think about, well, why grow them in space? I already talked about why we don't plan to take everything with us, because it increases mass. But when it comes to plants, there's another reason we don't take it with us already packaged. It turns out that foods, vitamins lose their potency over time. So we really do want to be able to grow what we need when we get there. But the other effect that we did not really count on is the psychological benefit. I talked about isolation for humans, and we've learned that the astronauts really enjoy seeing something living that's growing. They take packaged food now, but they really have enjoyed and said that it helps them to know that they can watch life. The plants also can help revitalize the atmosphere, and can, through the process of transpiration, actually, they can help produce water. So there are a lot of reasons why we take the plants and try to make sure that we can grow them in space. And if you go to the next page, you'll see these are just some of the pictures. Again, I talked about my team being involved. We have 2 habitats that are actually on the station, plant habitats. And one is called APH, for Advanced Habitat, and one is called VEGGIE, which is not an acronym. But these are examples of the astronauts, and if you just look at the smiles, we're always getting pictures, photos from them, excited about what we call a grow out on station and what's growing next. So just the smiles, and you see them just looking at, they said sometimes they just like to stick their head in and smell the soil or whatever is in there growing. So great benefit to the astronauts.
And I know this isn't in our questions, but I have confirmed there is real ice cream available in space. So I just wanted to throw out that
Yeah.
ice cream you see at the visitor centers is
Yes, yeah. There's all kind of experiments going on station now. Commercial payloads go up sometimes, and they look at how do you produce other foods and beverages in space. So there's some interesting things happening there. One of the other things that my team is doing is thinking about, when you think about growing corn and other vegetables, and I grew up family of gardeners, and my grandfather had gardens all over farms, actually. And you want to see tall corn and tall plants, but that's not so good when you're in a confined space where you don't have a lot of room. So part of the research that we're doing is trying to figure out how to make those plants grow in a compact form, but still provide as much fruit or as much yield as they would. And oddly enough, plants do react to the fact that there's no gravity. So they don't always grow straight up. They may grow sideways, or they may start to try to turn over. So there's a lot of research that we're doing, not just to understand how to get them to grow in the form that we need, but also how to provide nutrients. I saw the aquaponics in the back. We do think about how to limit the medium that we have to take with us, or that we will need on the moon or Mars to actually get them to thrive. These are some videos. My team is also involved, I mentioned, in the technologies that we're thinking about that we'll need on the moon and Mars. That first video is of a rover called Viper. It's actually going to be the first rover to go to the moon and land at the South Pole. Its mission will be to look for water. The Ames Research Center in California is actually responsible for the rover, but my team is responsible for that drill that's about to come out of the bottom, and actually it's going to be designed to go down into the regolith and pull back samples, and we're going to investigate those samples to see if there's evidence of ice or water. That's at the top, I guess your top left. On the top right, that's another part of my team. We're thinking about what does it take to operate on the moon, especially when some regions of it will be in permanent darkness. So my team built a simulation using data that's available to us to try to show which areas are going to be illuminated, which areas will be permanently shadowed, and also you're seeing the temperature map now. This is what we call low fidelity. We have some much higher fidelity simulations, but sometimes those simulations are being used for other efforts, and we needed something to plan. So sometimes low fidelity simulations are good to get quick answers when you are just trying to develop concepts. And my team is responsible for helping to develop the concept of how we would operate. If you think about a day in the life of being on the moon, what happens before the crew gets there? What systems do you need to be available? What happens when the crew arrives, and what happens after the crew arrives? One of my teams is responsible for helping to develop those concepts. At the bottom left is Razor. That is one of our robots in a bin that we have that has volcanic ash, which is very similar to the regolith properties. That robot is being developed to help us excavate regolith and to move it to an area where we can collect it. And then another part of my team is actually working on taking that regolith and turning it into some type of blocks. So we heat it up, a process called sintering, and use it to form pavers. Those pavers may be designed to build buildings, they may be designed to be a launch pad or a landing pad. One other member of my team is responsible for looking at, if you think about a lander coming in on the moon, it's going to kick up debris. We call that plume impingement. Early estimates are with the force of the engines coming down for the lander, it could actually create a plume that goes 2 miles up into space away from the moon. And think about that dust would then start to cover everything and create a bigger problem. So we're thinking about not only dust mitigation, but plume impingement mitigation. And one way may be to put down pavers for where that lander would come in. Part of the research with that robot is because you don't think about it, but when you see big rigs doing excavation on Earth, you see them digging, and they dig from one side. That's because we use the weight of the vehicles and gravity on Earth to create that momentum that allows you to dig. We don't have those kind of reaction forces. We won't have them on the moon. So this rover is actually digging and turning both ways to create the momentum that keeps it in place so that it can actually create the digging process. And then lastly, one of the other areas, and these are just a few, my team has 160 projects going on right now, so you're just seeing 4 of them. Everywhere humans go, Cindy was right. When we plan a road trip, the first thing my friends and family start talking about is, what are we going to eat on the way and what will we eat when we get there? We create trash. When you think about being in a space station, in a gateway, in a vehicle that is in transit out to Mars, we will create trash. You imagine going in your house and your doors are locked, your windows are shut, and you cannot come out for 9 months. What do you do with all that trash? This unit that you see, it's called OSCAR, and it stands for Orbital Syngas Augmentation Reactor, which is a great way to say trash to gas. And that's what we affectionately call this project. It is taking all the trash, everything from packaging to water, to edible mass that someone doesn't eat, to waste products from humans and other waste, and putting it in this chamber and heating it up to super hot temperatures. That's what you see happening, the combustion. And then we try to siphon off whatever can be reused. So it may be oxygen or other commodities that we can make use of. That's why we call it trash to gas. And we're hoping those gases can either be reused or we'll find a way to vent them from the vehicle safely. So those are just some examples of what my team is helping to do to get us ready to go back to the moon and Mars.
It sounds like you need to buy a big hat rack for your 160 projects.
We're busy.
Yeah. We have a number of educators here in the room with us. Can you, and they're eager to help point their students to careers in STEM. What can they do to help students contribute to space exploration?
The biggest thing you can do, being here, I think, I was busy, but when I was asked to come, I wanted to come because I firmly believe in STEM and inspiring kids to believe that they can. I can remember coming through as a young girl, and I had one teacher that was not very inspirational to me. I came through in an era where, as a black female, I was told by this teacher that I could be, as she said, it's too bad you're so smart, because the only thing you can be is a nurse or a teacher. And I remember thinking, and I said to her, I want to be a teacher too. But to inspire kids that whatever you want to do, teaching, we need teachers. You guys are vital. You start the process of helping them to understand and to have yourselves interested in STEM and to inspire them to be interested in STEM. That is massive from my standpoint. So anytime I get an opportunity to come out to talk to a group that's focused on STEM, I try to do it. Also, not just keeping them encouraged in STEM, but teaching them how to work in teams. Because as you heard me say, a lot of what we do, it's not based on an individual, it's based on teams working together. So those interpersonal skills are really important. When I went to college, and the last thing I'll say, I could work well by myself. I thought I worked better by myself, in fact, but I learned the value of teams. And I also learned the value of not just the science and math, which was my favorite, I lived for it, but I learned the importance of English. I learned the importance of all those other topics. So encourage them in STEM, but remind them they need everything else. I can remember the first time I went back to college and to one of my professors and said, now I know why you're making me learn that, because I thought I just needed the STEM subjects. They need it all. So just keep them encouraged in all their subjects and let them know that NASA needs them too.
Barbara, you're reminding me that I visited a school one time several years ago, and these kids were, the innovative thing that they were doing is working in teams every day, all day. And I asked a 6th grade girl who was, I guess she was like an average student, why do you think this is important to help you be successful in the future? And she said, because I've learned that sometimes it's appropriate to lead and sometimes it's appropriate to follow. And my jaw dropped to the ground. The 6th grader had clearly figured that out. So you can't
That's true.
echo that enough of why teams is so important in developing those skills.
That's absolutely true. I believe you can't be a good leader if you can't be a good follower. I just fundamentally don't believe it.
Yeah. So you talked about these different careers, and one thing I didn't mention this morning is NASA does have an internship program. There's a lot of availability for undergrads, but there is some for high school. So I would encourage you to share with your students NASA internships. You can just Google it; it'll come up every time. One of the silver linings in the pandemic was that federal agencies actually came together to solve the problem of how do we do internships now that everything shifted to remote work. And so we had a working group, NOAA, NASA, Highway Administration, and many, many others to offer virtual internships, and that went actually pretty well. And so now there's also virtual internships still available that NASA will continue to do, because we realize access is a critical issue and not everybody has a NASA center in their backyard. So, you know, when kids are asking questions about that, please let them know. We have in-person internships and we have virtual ones, and that may help them be able to participate a little bit more. I know we're holding them from lunch. Uh-oh. Does anybody have one burning question? Sal, can I do that?
No, it's on.
Oh. Hello, from PSA, District 6, in the house. Okay, so I've had several questions, as you know, even with Joseph this morning. One of the ones that pops up with both presentations today is the effect that radiation could possibly have on not only the humans, but you also mentioned taking up animals, and which animals would be the ones that go up there and provide the sustainability that we're looking for to have humans up in the moon and then going into Mars.
That research is being conducted out at the Ames Research Center. I actually worked for the Ames Research Center for about 12 years in the middle of my NASA career. And so I don't have the answer for that. They're still looking at it. And one of the things that they're investigating is, I talked about the nutrients, and we want to take as little as possible. So when they select the animals, it will be the ones that can provide the most benefit for a single animal. We're doing the same thing with the plants.
Anybody else? I have one question. Is related to that as well. So when we move to Mars and we colonize it and we live there, the human physical is going to change a little bit. Our heads are going to get bigger. We're going to be, is that the case? Is that going to happen?
So the biggest thing that we've noticed with humans on the station, for example, and even with the shuttle program, is the loss of muscle mass. Okay. So that's what we're working hard on. There can be effects to eyesight, but we have not seen any sense that our physical shape is going to change. It's just that our organs will react to what we're exposed to, and the lack of gravity. I'm sure I'm talking to teachers, so I know you know this, but when you're under less gravity, you know, less forces. So if we're on the moon, you'd weigh 38 pounds if you weighed 100 here. So that has an impact. If you're on Mars, you'd weigh 38 pounds, you weigh 90 on the moon. So that's really what we're working towards, to keep the human system functioning correctly.
And part of that's done through physical fitness. They have treadmills on the station. I don't know what other types.
Treadmills, bicycles, they have all types of weight equipment.
Yeah. Well, thank you everyone for your attention and great questions. Thank you, Barbara.
It's great to be here.